Welcome to the fifth lecture in this series on differential equations. Today we will do a chapter on homogeneous equations. So let's first begin with the requisite definitions as to what is a homogeneous domain. We will also define what is a positively homogeneous domain. We will look at some simple examples. We will look at homogeneous functions, positively homogeneous functions, and finally homogeneous differential equations and how to solve them. Alright, so let's begin with the definition. You see it on the slide. A subset D of the plane. We are always going to be looking at subsets of R2. A subset D of the plane R2 is said to be homogeneous if whenever you take a point xy in the domain D and multiply it by a scalar t not equal to 0, the point tx comma ty must again be in D. In other words, you see when you take a point xy in the domain, t times xy is simply a point collinear to xy with the origin. It is just a scaling of the point xy by a factor of t. The scaled point must also be in the domain. So you see that the scaling factor could either be positive or it could be negative. So as t varies over the real numbers, what happens to the set of points tx comma ty? It's a line. So a homogeneous domain is a union of lines except possibly for the origin. Origin may be removed because remember in the definition we are requiring that xy belongs to D implies tx ty belongs to D for t not equal to 0. So this is the algebraic definition of a homogeneous domain. Now let us see a few examples of homogeneous domains, but before that let's look at the picture of a homogeneous domain. Yeah, here you see a homogeneous domain shaded in yellow. It is the region between two lines y equal to x by 2 and y equals 2x. The region between these two lines has been shaded yellow in the first quadrant and the third quadrant. Now this union of these two yellow pieces is a homogeneous domain. Why is it a homogeneous domain? We can see that if you take a point xy in the yellow region multiplied by t, your t times xy is also there. So you see this is a point xy, you multiply it by t, you come to the collinear point tx ty if t is bigger than 0, and you come to this particular point on the opposite side if t is less than 0. So this is true for each such point. So this domain is a homogeneous domain. Now let's go further. Often we are not interested in a homogeneity with respect to all real numbers, but only with respect to positive real numbers. So likewise, let's define a positively homogeneous domain. When is a domain said to be positively homogeneous? If whenever xy belongs to D, t times xy, that is the point tx comma ty also belongs to D, but this requirement is only for t positive. In the earlier case, for homogeneous domain, we want t times xy should belong to D for all t not equal to 0. This time we are requiring it only for positive t. So let us call such a domain positively homogeneous domain. So we got homogeneous domains and we got positively homogeneous domains. So now let's look at an example of a domain which is positively homogeneous but not homogeneous. It's very easy to construct that domain. Look at here's a picture. The open first quadrant D equals the set of all points xy in the plane such that x is positive and y is positive. The open first quadrant. Why do I say it's open first quadrant? Because the boundary rays the parts of the coordinate axis which bound this quadrant are not included in the domain. The domain D is the set of all points x, y such that x is positive and y is positive. So, x equal to 0 is not included. So, it is the open first quadrant. This open first quadrant is obviously positively homogeneous, right? If I take x comma y in the open first quadrant, then Tx comma Ty will also be in the open first quadrant for T positive, but not for T negative. For example, 1 1, for example, the point 1 1 is in the domain, but take T equal to minus 2, and minus 2 is not in the domain. So, this is not homogeneous, but it is positively homogeneous. So, I hope you understand the distinction between a homogeneous domain and a positively homogeneous domain. Both concepts will be used repeatedly in what follows. Let us look at some examples of homogeneous domains and positively homogeneous domains. The entire plane is obviously a homogeneous domain. Take a point xy in the plane, Tx comma Ty is also in the plane. Next example is that the plane with the origin removed. I remove the origin from the plane. So, the punctured plane. Is it a homogeneous domain? Take a point xy, both cannot be 0, both x and y cannot be 0. So, either x is not equal to 0 or y not equal to 0. Multiplied by t, where t is any real number which is not 0. Then Tx comma Ty cannot both be 0 because t is already not 0, and we know that x or y is different from 0. So, this domain R2 minus the origin is a homogeneous domain. The first quadrant, as we have seen, is a positively homogeneous domain which is not a homogeneous domain. Instead of that, now let us take the next example. Let us take the first quadrant and the third quadrant, like that yellow, similar to the yellow regions in the very first slide that we took, those two pieces, those two yellow pieces that we took. The first quadrant and the third quadrant, that is homogeneous domain. Now let us take the function f of xy equals logarithm of mod x minus y by x plus y. Where is this function defined? This function is not defined along the line y equal to x, and this function is also not defined along the line y equal to minus x. So, take the plane, remove these two lines, and then you get 4 pieces. The union of these 4 pieces is a homogeneous domain. If you take a point xy and multiply it by t not equal to 0, again the point Tx comma Ty will be in one of these 4 pieces. The last one is a little exercise for you. Examine whether the set of points in the plane xy such that x bigger than y, you would like to call it the open half plane. Is this open half plane homogeneous? Is it positively homogeneous? Okay, think about that, it is not difficult. So, these are some examples of homogeneous domains. Now, let us come to the main point of this chapter, homogeneous functions and homogeneous differential equations. So, when is a function said to be homogeneous? First of all, it should happen that the domain should be a homogeneous domain. That is, whenever xy is in the domain of the function, Tx comma Ty must also be in the domain of the function. Otherwise, the definition would not make sense. That is exactly why we defined the homogeneous domains before embarking upon defining a homogeneous functions. So, a function f of xy is said to be homogeneous if f of Tx comma Ty equals t to the power k times f of xy. So, the right hand side and the left hand side are both defined because whenever xy is in the domain, Tx comma Ty is also in the domain. This K is called the degree of homogeneity. This K is called the degree of homogeneity, and we will say that f is homogeneous of degree K. So again, let us take the number of examples. X squared plus y squared minus 7xy. It is homogeneous of degree 2. If you replace x and y by tx and ty, you see the factor of t squared coming out. F of tx comma ty will be t squared times f of xy. It's directly possible for you to check this. Now let's take the next example, tan inverse of y by x. Now this function is not defined when x is 0. So it is not defined along the y-axis. So remove the y-axis. And then you see that when you replace xy by tx comma ty, nothing changes. Tan inverse of y by x is the same as tan inverse of ty by tx. In other words, f of xy equals f of tx comma ty. So this is a function which is homogeneous of degree 0. This is homogeneous of degree 0. Let us take the third example. Square root of x cube minus y cube. Now we are looking at real valued functions only. So from the domain, we have to remove points like 1 comma 2. Because when I take x equal to 1 and y equal to 2, the quantity under the square root becomes negative. We don't want that. So what is the domain of this function? The domain of this function is a set of all points x, y in R2 such that x is bigger than y. It is a half plane. So this domain is positively homogeneous but not homogeneous. So you say that this function is positively homogeneous of degree 3 by 2. What is the positively homogeneous function? The equation f of tx comma ty equal to t to the power k times f of xy should hold for t positive. There is an equation, the displayed equation f of tx comma ty equal to t to the power k times f of xy must hold for positive values of t. So you say that this function is positively homogeneous. So the last example that you see in the slide, square root of x cube minus y cube divided by x squared plus y squared to the power 3 by 2. You replace x and y by tx comma ty, and then you see that it's homogeneous of degree 0, but t has to be positive. So you got examples of functions which are homogeneous and functions which are only positively homogeneous. So what kind of domains are we going to look at for functions? We are going to be looking at functions f of xy, m of xy, n of xy. 3 functions frequently occurring in differential equations. mxy dx plus nxy dy equal to 0 will be the differential equation, right? So m is a function of x and y and n is a function of x and y. What are the domains for m and n? The domains will have to be either homogeneous or positively homogeneous. So what kind of domains are we going to be looking at? Mostly the entire plane. Many examples will have the entire plane as the definition. Open half planes, like the last example that you saw, square root of x cube minus y cube appears. So you need to look at half planes. The open first quadrant, this is a very important example, the open first quadrant, and finite intersections of open half planes described in item number 2 above. So these are the kinds of domains that we are going to be looking at. Mostly R2 minus the origin, R2, the whole plane minus the origin, a half plane, a quadrant. So such domains we are going to be looking at. They are all homogeneous or positively homogeneous. Now let us take up the definition of a homogeneous differential equation. Assume that m of xy and n of xy are both defined on a homogeneous subset D of the plane, and m of xy and n of xy are homogeneous of the same degree. That is, m is homogeneous. If m is homogeneous of degree 2, you want n also to be homogeneous of degree 2. If m is homogeneous of degree -3, then n must also be homogeneous of degree -3. So, the degree of homogeneity of m and n must be the same. Then you say that this differential equation mxy dx plus nxy dy equal to 0 is a homogeneous differential equation. So, let us look at two examples of homogeneous differential equations. The first one is x squared minus y squared dx plus 2xy dy equal to 0. Observe that the m here is x squared minus y squared, the n here is 2xy. They are both defined on the entire plane and they are both homogeneous of degree 2. So, the first differential equation is homogeneous. What about the second differential equation? The second differential equation is log x squared minus log y squared. Immediately if x is 0 or if y is 0, there is a problem. So, we have to remove the x axis and we have to remove the y axis. We are getting all the open quadrant, the open first quadrant, second quadrant, third quadrant and fourth quadrant. The union is a homogeneous domain. So, replace x by tx and y by ty. What happens to log x squared minus log y squared? It is log of x squared by y squared, and then you got the second term tan inverse of y by x. When you replace y and x by ty and tx respectively, the t cancels out. So, both terms are homogeneous of degree 0. So, the second equation is also a homogeneous differential equation. As per this definition, the following equation would not be homogeneous. Let us look at equation 2.1. X plus y dx minus square root of x squared plus y squared dy is not homogeneous. Why is it not homogeneous? Look at the first term, m of xy. M of xy is x plus y. It is homogeneous in the entire plane of degree 1. What about square root of x squared plus y squared? Replace x by tx and y by ty. What happens? Tx squared plus ty squared under root is under root t squared into under root x squared plus y squared. But under root of t squared is mod t. F of tx comma ty is mod t times f of xy. So, the function square root of x squared plus y squared is not homogeneous, it is only positively homogeneous. So, the nxy term here is not homogeneous, it is only positively homogeneous. You would like to call this differential equation as a positively homogeneous differential equation naturally. You wouldn't want to call it a homogeneous differential equation, you would like to call it positively homogeneous because it is homogeneous only when t is positive. Let us take another example. Square root of x squared plus y squared dx plus square root of x squared minus y squared dy equal to 0. So, let us say that this differential equation is taken on x bigger than y, the half plane x bigger than y. Not only we take x bigger than y, we also take x and y to be positive. So, in this 2.2, we shall add a further condition that x bigger than y bigger than 0. Okay. So, let us make that additional assumption. Then x squared minus y squared will be positive if x is bigger than y bigger than 0. So, the domain on which x squared minus y squared is defined is positively homogeneous. So, the second term is not homogeneous, it is only positively homogeneous. The first term is not homogeneous, it is only positively homogeneous. The second term fails to be homogeneous for two reasons and the first one fails to be homogeneous for a single reason, namely mod t comes out. In the second case, not only does mod t come out, the domain on which this term is defined is only positively homogeneous. I'd like to draw your attention to the fact that most books will call 2.2 also as a homogeneous equation. We have been slightly careful, we have distinguished between a homogeneous equation and a positively homogeneous equation. So why do books call 2.2 also as homogeneous? Reason is very simple. Whenever we are in situations like 2.2, we simply assume that everything is happening in the first quadrant. So that's a tacit assumptions that books make, which is why they don't get into any trouble. So in the first quadrant, the method that we will apply for homogeneous equations is identical to the method which we apply to positively homogeneous equation. As far as the method of solution is concerned, they are the same if we restrict ourselves to the first quadrant. But if you try to solve equations which are positively homogeneous but not homogeneous in a quadrant other than the first quadrant, you need to exercise some care, and we look at some examples as we go along. So in short, the method that follows works for positively homogeneous equations as well as homogeneous equations in the first quadrant, whereas if it is a homogeneous equation, then you don't have to worry about the first quadrant, it's valid throughout the domain. So that's the reason why books don't distinguish between them, because they will assume that when the equation is not homogeneous or only positively homogeneous, they assume tacitly that we are working in the first quadrant. We have been a little cautious, paying attention to details. Just a disclaimer, just to keep things simple, we shall assume, unless otherwise stated, that if the differential equation is only positively homogeneous, then the domain is either the first quadrant or a positively homogeneous subset of the first quadrant. Alright, so now we come to the celebrated y equal to Vx substitution. Right in the first lecture, I mentioned this y equal to Vx substitution. The idea goes back to Leibniz around 1693. You will see this name appearing right in the first lecture, and you will see this substitution y equal to Vx being mentioned there. So theorem 1, the substitution y equal to Vx transforms a homogeneous differential equation into a variable separable equation. That's the reason why homogeneous equations are nice, because through a very simple substitution you can reduce it to a variable separable equation. The same holds also for a positively homogeneous equation, as long as we stick to the first quadrant. Let's look at the proof. Y equal to Vx. So apply the product rule, dy by dx equals V plus x dv by dx. Simple application of product rule gives you equation 2.3. So substitute into the differential equation. Take the differential equation to be mxy plus nxy into dy by dx equal to 0. What is the assumption? M and n are homogeneous of the same degree k. So put y equal to Vx in this equation. What do we get? We get m of x comma Vx plus n of x comma Vx into the dy by dx has been replaced by v plus x dv by dx. Well, m and n are homogeneous. So m of x comma Vx will be equal to x to the power k times m of 1 comma v. N of x comma Vx will be x to the power k times n of 1 comma v. The x to the power k becomes a common factor from both terms and it comes out. And I am going to divide by x to the power k. And a little rearrangement will give you a variable separable equation. That is the proof. What happens if the differential equation is only positively homogeneous Then in that case, remember, we work in the first quadrant, and in the first quadrant x is positive. And again, m of x comma vx will be x to the power k times m of 1 comma v. So the proof simply goes through as long as we are in the first quadrant. That's what I mentioned. So the method of proof goes through identically in the first quadrant for both cases. Without further ado, let us move on to the examples. The first example, 2xy dx minus x squared minus y squared dy equal to 0, equation 2.4. If you go back to the previous lectures, you will see that we have encountered equation 2.4. Equation 2.4 is a differential equation for the family of circles touching the x-axis at the origin. And I said you don't solve the differential equation right now, we have to wait until we move on to the chapter on homogeneous equation, and here we are. Now we are in a position to solve this differential equation 2.4. We employ the substitution y equal to Vx and we use equation 2.3. 2.3 says dy by dx is v plus x dv by dx. It is convenient to rewrite 2.3 in a much easier form, dy equal to v dx plus x dv. Just write dy as v dx plus x dv. Just for simplicity, it's much easier to do so. At least in writing is easier. So we simply substitute y equal to Vx, this becomes a 2x squared v dx, x squared minus y squared becomes x squared into 1 minus v squared, and then the dy is v dx plus x dv. The x squared cancels out and then we are left with 2v dx minus 1 minus v squared v dx minus 1 minus v squared x dv. Simplify, you get 2.6. Look, the differential equation is variable separable, v cube plus v dx plus v squared minus 1 x dv equal to 0. It's a very easy to solve this differential equation. Simply divide by v cube plus v, simply divide by x. What do you get? You get dx upon x plus v squared minus 1 upon v cube plus v dv equal to 0. So it's a very easy matter to solve this differential equation by employing partial fractions. You know how to do that, so I leave it as first exercise. Do the routine partial fractions calculations and obtain the solution of 2.6 is v squared plus 1 into x upon v equal to c. And then what is v? V is y upon x. So put in the value of v and you get this equation, x squared plus y squared equal to cy. The orthogonal trajectories are circles touching the x-axis at the origin. That was what we expect from geometrical considerations, and that was what I said in the last lecture. So we have done the problem completely now. Let's move on to the next example, orthogonal trajectories again. So find the orthogonal trajectories of the system of curves x cube minus 3xy squared equal to c. So how do you do that? Differentiate the equation, c straight away disappears. What do you get? 3x squared minus 3y squared minus 6xy dy by dx equal to 0. The 3 factors out and you get a simple looking differential equation. The astute student will recognize that x cube minus 3xy squared is a real part of z cube, where z is a complex number x plus iy. And no prizes for guessing what would be the orthogonal trajectories. I am pretty sure the students would have guessed what the orthogonal trajectories are. I won't tell you, guess, and guess correctly please. Okay, so differentiate, the c disappears as I said. You get the differential equation x squared minus y squared dx minus 2xy dy equal to 0. What is the differential equation for the orthogonal trajectories? Go back to the previous lectures and you figure it out. It's x squared minus y squared dy plus 2xy dx equal to 0, right? That's a homogeneous differential equation. M is 2xy and n is x squared minus y squared. It's homogeneous in the entire plane. And so the y equal to Vx substitution has to be employed, and you can simply carry out the details to completion. So please do it and then check whether you have guessed correctly. So again we have got another example of orthogonal trajectories coming from complex analysis, but we have applied the theory of differential equations to understand it. Now more examples. Let us look at an example in the first quadrant. Let's look at an example in the first quadrant. Because it's going to be only positively homogeneous, we see a log x and a log y present. So automatically x has to be positive and y has to be positive. The differential equation is defined only in the first quadrant. And the first quadrant is positively homogeneous but not homogeneous, but that's okay. So your differential equation is a positively homogeneous differential equation 2.7. Replace x and y by tx and ty respectively, and you see the things are homogeneous of degree 1, positively homogeneous of degree 1. So let us also ask for the solution of this differential equation satisfying the condition y of 1 equal to 1. That is, the solution of 2.7, remember, is a family of curves, and one of those curves will pass through the point 1, 1, and you are asked to find which one of these curves is it. So think of x as a function of y. So think of x as a function of y, and we will write x of y. X is a function of y, so we will write x of y, and y is the independent variable. The differential equation is easily seen to be positively homogeneous, and you can use the substitution y equal to Vx, and we will get the Vx equation, the v dx plus log v into v dx plus x dv equal to 0. The usual routine you go through. So you get a variable separable equation. What is the variable separable equation that you get? That is equation 2.8 that is displayed in the slide. Equation 2.8 is easily seen to be variable separable. Separate the variables, integrate it. When x is 1, y is 1. So what is the value of v? V is also 1. So to integrate 2.8, you could employ definite integrals, because definite integrals incorporate the initial conditions in the solution process. Or you can apply indefinite integrals if you will, but you can certainly solve it in whatever way you want. I employed definite integrals and I got an easy integration. So you do this integration and you get equation 2.9, log y minus log of 1 plus log y minus log x is 0. So one of the logs can be removed by exponentiating. You get y equals 1 plus log y minus log x. That is equation 2.10. So 2.10 describes the solution curve of our differential equation 2.7 passing through the point 1, 1. Well, one could stop here and say, okay, we have solved the differential equation, what more do you want? But I would like to know how to sketch this curve, how to sketch the solution curve. It's of interest to do that. So how do we do that? Well, first of all, observe that the differential equation gives the value 0 to the derivative dx upon dy. Remember, I said think of x as a function of y, and so compute dx upon dy. Dx upon dy will be what? Look at equation 2.7. Look at equation 2.7 and compute dx upon dy at the point 1, 1. What will happen? The log y minus log x term becomes 0. So dx by dy is 0. This is exactly the reason why I said we regard x as a function of y and not the other way around. So now we got x prime of 1 is 0. The derivative of x is 0 at y equal to 1. So it's of interest to know whether this point y equal to 1 is a point of local maximum, is it a point of local minimum, or what is it? When you want to do curve sketching, this point becomes important. Points of maxima, minima, points of inflection and stuff like that. So we must compute the second derivative, x double prime of y. Now you will say, your initial impulse would be to say, take equation 2.10 and do an implicit differentiation. Start from 2.10 and do an implicit differentiation and compute d2x by dy squared, but I urge you not to do so. Instead, I want you to use the differential equation as much as possible. Don't use the solution, use the differential equation to the extent possible. So let us see how to compute the second derivative from the differential equation directly and answer the following questions. Is y equal to 1 a point of minimum, a maximum, or a point of inflection? Is there a value of y bigger than 1 at which the derivative vanishes? How many points of maxima, minima are there, if you like? Can you say something about the function x of y, whether it is increasing or decreasing, monotonicity properties of this function? Sketch the graph of the function x of y near the point 1, 1. Do you think x of y would tend to 0 as y tends to a for some positive a bigger than 1? What happens as y goes to infinity? So these are the natural questions that you discuss when you want to do curve sketching. Okay, so let's go back to the first question, how to compute the second derivative directly from the differential equation. It's important to do that. I'll come back to this point again later. It is important to get as much information as you possibly can directly from the differential equation without solving the differential equation. Why? Because differential equations that arise in real life cannot be solved completely. We know that. And so these are only toy problems that will teach you how to deal with differential equations. The real problems are much more complicated. So we must try to use these toy examples and try to do those things which you will actually do in real life. Namely, without using the solution, directly from the differential equation, glean as much information as you possibly can. So let's start with the first thing, inquire whether 1 is a point of maxima or a minima for the function x of y. You have to compute the second derivative where at the point y equal to 1. So let us take the first derivative, the differential equation dx by dy when rearranged gives you x into log x minus log y upon y. Go to the differential equation, it is written as m dx plus n dy equal to 0. So get your dx by dy. Dx by dy will be minus n upon m. Write that down. That's what we have done. It is x into log x minus log y upon y. So we must differentiate this expression with respect to y using the product rule and quotient rule. When you use the quotient rule, what happens? You will be getting a y squared, you will get an ugly expression. You will get an ugly expression with a y squared in the denominator. But we are computing the second derivative at y equal to 1. So the denominator will become 1. So I am only interested in the numerator. I don't even have to write the denominator. Also, when you want to compute the numerator of the derivative, what happens? It is going to be y times the derivative of the numerator minus the numerator times the derivative of the denominator. So that's what I'm saying. It's y times the derivative of the numerator. What is the derivative of the numerator? there are two terms and you use the product rule. So, yx into d dy of log x minus log y minus x into log x minus log y times the derivative of y, plus there is a third term plus x prime into y into log x minus log y. That term has not been written here in the next line. Why have I not written? Is it because I made a mistake? No, I have not made a mistake. X prime of 1 is 0. So, that term is going to drop out. So, there is no need to write that term. So, I have not written the term x prime of 1 because it is going to drop out. So, I have two terms here and x is 1 and y is 1. So, what is d dy of log x? It is x prime upon x, but again x prime is 0 at y equal to 1. So, that term also drops out. Next term, d dy of minus log y, that is minus 1 because y is 1. And here in this term you put x equal to 1 and y equal to 1, the log x minus log y term disappears. So, the second derivative at 1 is minus 1. Notice that we have not used the solution at all, we have directly worked with the differential equation and we have got the important piece of information that the point y equal to 1 is a point of local maximum. And so, you know how the graph should look like near a local maximum. Let us start drawing the graph. Now, we have enough information for us to draw the graph. Here we have the graph. Notice that we are looking at x as a function of y. So, really we should be doing the graph like this, we should be drawing the graph like this. But never mind, I already have the graph drawn and the horizontal axis is the x axis and the vertical axis is the y axis. So, x is a function of y and so you see that the point 1 1 is a local maximum. So, the graph must look like this near the point 1 1. So, we have answered the second question in the exercise, draw the graph of the function solution curve near the point 1 1. Now, let us ask, why have I continued the graph like this and why have I continued the graph like this? The next question that I want to know is that if y increases, according to this graph the x will decrease. As y becomes larger and larger, the x value comes close to 0. And then when y increases from 0 to 1, the x value will increase from 0 to 1. In other words, x as a function of y increases over here and decreases over here. How do we know that? First thing to do is that again go back to the differential equation. What does the differential equation give you? The differential equation gives you x prime of y equal to log of y by x upon minus of y by x. So, x prime has no other roots. You see, we are looking at the first quadrant only. xy has a local maximum at y equal to 1. So, what is the meaning of saying that it has a local maximum at y equal to 1? So, when y becomes larger than 1, the x value becomes smaller than 1. Because at y equal to 1, the value of x equal to 1. So, let me see. Notice that if x at the value y equal to 1, we know that the x equal to 1. Okay. So, y equal to 1 is a local maximum. So, if y increases beyond 1, then x must decrease. It is a local maximum. So, 1 is a maximum value. So, when you go beyond the maximum value, the value of x has decreased. If the value of x has decreased, that means what, x is going to be less than 1 and y is going to be bigger than 1. So, what is log of y by x? So, y by x is bigger than 1. So, log of y by x is positive. So, what happens here? So, you see x prime of y is log of y by x upon minus of y by x. Remember that we have just seen that the numerator is positive and we are in the first quadrant. So, the denominator is negative. So, the derivative is negative beyond 1. So, as a result, xy continues to decrease as y increases beyond 1. So, y by x So y by x must be bigger than 1, and therefore log of y by x must continue to be positive, and so the derivative continues to be negative, and so the x of y is strictly monotone on 1 infinity. And similarly, you can see that it must increase from 0 to 1. So that is why the graph has been drawn this way. Now the question is, how do I know that this graph goes all the way to the origin? How do I know that when y goes to 0, x must go to 0? And how do I know that when y goes to infinity, x must go to 0? Here we will have to go back, at this stage we will have to go back to equation 2.10. Here we go back to equation 2.10 and look at this equation, y equal to 1 plus log y minus log x. Suppose if y goes to infinity, then what happens? The left hand side goes to infinity. Now bring the log y to the left. When y goes to infinity, what can you say about y minus log y minus 1? What can you say about y minus log y minus 1? That will also go to infinity. Let me again do this for you on a sheet of paper. What do we have? We got y minus log y minus 1 equals minus log x. So when y goes to infinity, is it correct to say y minus log y minus 1 also goes to plus infinity? How? If you believe this, that means if so, then minus log x must go to plus infinity, so x must go to 0. Why is this true? Why do I say that y minus log y must go to plus infinity? Because you see, when y goes to infinity, log y also goes to infinity. So isn't this an infinity minus infinity kind of an indeterminate? So how do I casually say that y minus log y goes to plus infinity? We can see that y goes to infinity faster than log y. Y goes to infinity faster than log y, therefore y minus log y will still go to plus infinity. Let's look at the exercise that I given you on the slides. So to think about this exercise, let us take a look at equation 2.10, y equal to 1 plus log y minus log x. Note that x must tend to 0 as y tends to infinity, the last part 3D. As y goes to plus infinity, it must happen that x must go to 0 plus. Otherwise, the right hand side of 2.10 would go to infinity slower than the left hand side, which is a contradiction. Or in other words, bring the log y on the left hand side and you can argue as I argued before. So basically what am I saying? We are saying that certain things go to infinity faster than certain other things. Log y goes to infinity faster than log y. Y goes to infinity faster than log y. Y squared goes to infinity faster than y. E to the power y will go to infinity faster than y. So what do you mean by all these things? So here is an exercise. Discuss this last part precisely. What does it mean to say that a function f of t tends to infinity slower than g of t, where f and g are defined on the same interval containing a and t goes to a? So what would be an appropriate definition? We could say that ft goes to infinity slower than gt if the ratio ft by gt goes to 0. In the present context, can you prove that log y goes to infinity slower than y by applying the L'Hopital's rule, for example? But the same logic, log t to the power 1000 will go to infinity slower than t to the power 1 upon 10,000. Generally, no matter how large your n is and how small positive your a is, log t to the power n will go to infinity slower than t to the power a as t goes to infinity. So, this fact about comparing the growth at which two functions, the rates at which, comparing the rate at which two functions go to infinity is extremely important in calculus. I repeat, it is extremely important in calculus to know how fast one function goes to infinity relative to another function, or how fast does one function go to 0 relative to another function. You could have a ratio f upon g, both f and g may go to infinity or both of them may go to 0, but which one does faster? Calculus in essence is the comparison of the growths of functions relative to one another, either growth to infinity or decay to 0, whichever is the appropriate case. It must be noted that given two functions ft and gt, the question of whether ft goes to infinity faster or gt goes to infinity faster is usually not easy. It is easy in the case of log y and y because you can straight away apply the L'Hopital's rule, but often you are not going to be so lucky to apply L'Hopital's rule, and the problem is going to be pretty hard to decide which one goes to infinity faster, or do the two functions go to infinity at the same rate. As an example, let us take the function ft to be the number of primes in the interval 1 to t. So, suppose if t is 10, then f of t is 4. There are 4 primes, 2, 3, 5 and 7. Similarly, if t is 100, f of t is the number of primes between 1 and 100. And you know that the number of primes goes to infinity with t. The number of primes is infinite. So, f of t goes to infinity as t goes to infinity. Let us look at another function gt equal to t upon log t. T upon log t also goes to infinity as t goes to infinity. Apply L'Hopital's rule. We have just seen that t goes to infinity faster than log t. But what about the ratio ft by gt? Does ft goes to infinity faster than gt, or is it the other way around, or are they going to infinity at the same pace? This question was a notorious conjecture by Gauss and Legendre. Gauss and Legendre independently conjectured that ft and gt go to infinity at the same rate, but this conjecture remained unproved for nearly 100 years. It was settled independently by two French mathematicians, one in 1896 by Hadamard and the other one in 1898 by de Laval-Poisson. And this theorem is called the prime number theorem. It's one of the most remarkable theorems in number theory. So, you see that comparison of infinities is not an easy task. And the idea of comparison of infinity has been beautifully expounded by G.H. Hardy in this little tract called Orders of Infinity. We will take now another example, but we shall probably do this in the next lecture. We will take this innocent looking differential equation dy by dx equal to y upon 1 plus y into x. This is a variable separable equation, and we can actually find the solution. Again, the solution will present itself in implicit form, and what we want, as we have done in this example, we want to understand what happens when x goes to infinity, how does y go to infinity. We will take this up next time. We will stop here for today. But meanwhile, you can solve equation 2.11 and be ready.